Welcome to homework.
The binding energy can be thought of as the ground state energy minus the electrostatic potentials. We're given a covalently bonded hydrogen molecule, so this is a bit of what it looks like. So a proton-electron system on both sides. And we know that for when observing the potentials, we think about the electron as being in the middle, and we're given the separation between the two protons. And we can call this R0. Just remember that when we're using the radius later on, we want half of this distance, as the electron is shared between both protons. So let's look at the electrostatic potentials. This can be broken down into two interactions, the proton-proton interaction and two electron-proton interactions, because there are two electrons. So let's look at the electron-proton interaction for now. The formula for electrostatic potential is given by the two charges over 4 pi epsilon naught, which is just some constant, and the radius between them. Okay, so in our case, the charges are the same, so this becomes the charge of the electron all squared divided by the constants and the separation. And remember, we want half the separation, where nanometers is times 10 to the minus 9 in standard form, 4 meters. And then we want to multiply this value by a third, because given in the question, we know that they spend a third of their time midway. And this is equal to roughly 2.06 times 10 to the minus 18 joules. And I think we'd rather have this value in electron volts. So the way we go from joules to electron volts is to divide by the number of joules in 1 electron volt, which is 1.6 times 10 to the minus 19 joules per electron volt. So this is the same as 12.88 electron volts. Now is a good time to mention that because the electron-proton interaction is attractive, this potential is negative. So the final answer is negative. Okay? So moving on to the proton-proton interaction. We have a similar calculation. Both the protons have the same charge. But instead of using half the separation, we can just use the value given to us, 0.074 times 10 to the minus 9. And this is roughly equal to 3.09 times 10 to the minus 18 joules, which, given our conversion from before, we can rewrite as 19.33 electron volts. Okay? And the proton-proton interaction is repulsive, so they push each other away, so the potential is positive. Now we can look at the ground state of the molecule. And the molecule is made up of two hydrogen atoms, right? And the ground state of a hydrogen atom you should already know, or it can be given to you in the textbook. And this is given by E0, and that is 13.6 eV. So now we know how to calculate the binding energy, and we have everything we need. So the binding energy can be thought of as two lots of the ground state energy. Two because the molecule is made up of two hydrogen atoms. And I should just make explicit that this is the ground state for one hydrogen atom. And then we want to take away the electrostatic potentials. So we have plus 19.33 minus 2 lots of 12.88. This should be minus. That should be positive, sorry. So the reason I've explained before, the reason why there's a 2 inside the inner brackets is because there are 2 electrons. And the reason this is multiplied by a further 2 is because both electrons are being attracted by 2 protons. So you get double the interactions. And once we calculate this, we get 4.99 electron volts. Now, some of you may have a slightly smaller answer due to your use of units and decimal places and significant figures. As long as you get an answer between 4 or 5 electron volts, you should be correct.